And our learning objectives for today are to define and explore different mechanisms for runoff. So we're going to do some conceptual stuff. And then we'll talk about the curve number method, which is one method for determining the runoff volume of a watershed. All right. Yeah, so let's just review this idea of infiltration into soil. And what we've talked about last week was how if we have Z depth below the surface of our soil here, and then theta I is the soil moisture in the soil. And over time, as it's raining, we get water infiltrating down into the soil. And then this is kind of the profile of soil moisture where we get up to saturated here. So over time, the soil will become saturated at the surface, and then that saturation kind of moves down slowly over time. What we talked about is that if the rainfall rate is less than the infiltration rate, then all that water is going to go down into the sea. It is less than theta, or whatever the infiltration rate is, then we're infiltrating. And at some point we get saturation at time 4, so that's saturation at the surface. And then we begin to get runoff, right? So the infiltration rate goes down over time, and whatever isn't infiltrating is going to run off and pool and kind of, make its way down to creeks and stuff like that. So here's just a look at the time frame of what infiltration might look like before, during, and after rainfall. Here is the gray is a soil moisture profile. So saturated is up here, 0 is up here. So we have wet soil, it's not saturated, right? And then as you go down and get close to this water table, you become saturated. This is where the capillary fringe would be. I'm just going to do a laser pointer. Okay. This would be our capillary fringe, so it's a little bit saturated above that water table. The water table is going to go and intersect with the stream. And so where that water table intersects with a stream, that's going to be your base flow. The base flow is getting water just from groundwater, right? There's no surface runoff. Now we get rain, and so we start to get this kind of new wedge of water coming in. So this darker gray is the soil moisture coming in from rainfall, and that's going to bump up the soil moisture here. And so you get base flow, but you also get what's called subsurface storm flow. And the idea is that the water table is going to bump up just a little bit. You see this little hump right here? As that water table bumps up, as this kind of infiltration happens in the near term, the gradient between the water table and the stream increases. And when that gradient increases, we'll talk about this for groundwater section, you basically just have the ability to have more water enter into the stream. So the base flow is going to bump up. And then in the next stage, we're going to get saturation. So the surface is becoming more saturated, and you get a couple things now. So base flow, subsurface storm flow, that SSSF. You can get what's called direct precipitation onto a saturated surface. So if it's all wet right here at the surface, any rainfall that comes on that is going to just run right off. This is going to be like pavement, even though it might be dirt or grass or whatever. So direct runoff. And then you also get return flow. So water can actually exit the water table. The water table is so high now near the stream that water can actually flow out of the ground and go into the stream. So now you have 4 different mechanisms here. So we have just situations in Colorado like this, and wet meadow is a great example. You might see some of these. I think this is a Gunnison Basin, where it's a swale. It's not quite a creek. It's a swale, and when you have, like in the springtime, lots of water entering the soils from the hill slope from melting snow, it can flow on the surface here. So you have surface flow. But you also have kind of, if you were to walk here, it'd be squishy, right? So it's going to be saturated soil. So any rain that would fall in this area would directly run off into that wet meadow. Wet meadows are super important for habitat as wetlands, especially for sage grouse. And so here's a bunch of people looking at a wet meadow in this rangeland in the Gunnison Basin. We can look at what saturation looks like visually from a plan view. and over a storm event. And so the darker would be saturated soils, the gray would be maybe less saturated soils. And you can see that this isn't a creek, it's just kind of a little watershed. And you've got some swales or some low areas that are wet. Oh, sorry. And so the dark would be kind of before a storm event, and then as it rains, that saturated area extends up further uphill, and you get a larger area. You could also see this seasonally. So in the summertime, you've got a smaller area that's going to be saturated, and maybe in autumn it expands, and then in the spring and winter times that might be a much bigger area. All right, so let's draw that kind of hill slope again, and we'll have kind of the surface that goes down a hill, flattens out into a floodplain, and then maybe we get a little creek, something like that. So that's our water surface. It's intersected with the water table, which kind of comes up like this. So we get rain coming down, and there's a lot of different pathways. So let's list all these pathways out. So the first thing that could happen is it goes in the soil, and maybe it just makes its way all the way down into the groundwater. So we'll call that pathway number 1. And that's going to be groundwater. It's going to ultimately contribute to groundwater flow rate, or like deep infiltration. We could also have it go into the soil and start to make its way downhill. We'll call that number 2, which is known as shallow subsurface flow. And in order for water to flow horizontally like this, the water table needs to be much higher. So we have to actually intersect. We have to have kind of saturated, or we'll just say, actually I'll do this. We'll just say saturated conditions. Because you can imagine if you have a kind of a pit or a column of dry sand and you put water on it, you sprinkle water on it, that water is just going to go down. There's no reason for it to go sideways. And so for things to go sideways, you actually need to have mostly saturated conditions that allow water to move horizontally, connectedly all the way down to a water table, or sorry, a stream or something like that. And I'll note that once water hits the water table, it's now going to flow towards a stream with the gradient of that stream. So we can also have 2 different types of runoff. And so runoff just simply means it's going to run off the soil, off the surface. And so the first one I'll talk about is, I'll just say number 3. And that's going to be called infiltration excess. And that's kind of what we've been talking about, where the infiltration capacity is exceeded by the precipitation, and therefore we get overland flow. Overland just means on the surface. This is also known as Hortonian. Horton was a hydrologist who, kind of published on this process. And then the final type, which we've already talked about, is when that water table is high, right? The water table's been elevated now because we've been raining, and now we're kind of, maybe we're more in flooded conditions, or this is saturated. We'll just say this is saturated ground right here. And so if we get rainfall falling on this area, call that number 4. It's called saturation excess. Saturation excess overland flow. So we've become saturated. We're falling on that saturated soil, which acts like pavement, and it just runs that water right off. Sometimes this is called, less commonly, Dunnian flow, after Tom Dunn, who published a lot on this.
What's the difference between 3 and 4? How both soils kind of saturated?
So you don't have to have saturated conditions for infiltration excess. So the idea of the saturation excess is it's really going to be a limited area, like where we have those swales where they're just going to be wet because the water table kind of comes up to the surface. Does that make sense? So as you rain, like if you think about a stream rising with water, potentially the groundwater, there's a lag, the groundwater moves more slowly, but the groundwater table near the stream is coming up as well. And so if you have these saturated areas along the valley and whatnot, I'll just go back to this image. This is where the saturation excess overland flow would occur in these areas along a stream. So swales, valley bottoms, that sort of thing. Anywhere that you would walk and it'd be kind of squishy, right? That's where saturation excess overland flow is going to happen. Infiltration excess overland flow could happen anywhere in the watershed based on the fact that the rainfall is in excess of the infiltration capacity of the soil. So you could have clay that's not saturated, right? And you could imagine that in an extreme case, clay is going to absorb a very little amount of rainfall over time because it's slow. So if you rain on clay, for example, the Book Cliffs, you're going to have infiltration excess overland flow everywhere because nothing's really going in that soil, at least over the course of an hour rainfall event. Great question.
So does saturation excess mainly depend on where the water table's at?
Yeah, exactly. And again, it's going to be linked to those low-lying areas near streams and drainage ways. The desert, you're not going to see so much of that in the desert. If you go up to mountains, like I showed that meadow up in Gunnison Basin, areas where you have more vegetation, more soils, that's where you're going to see. You're not going to see a lot of like low-lying washes, necessarily that are going to be wet here. Although, there's some examples of that. So we have those 4 pathways, those 4 kind of main pathways to talk about. Let's talk about them in terms of how quick things run off. So we have, first we'll say quick flow. And that's going to be anything that has to do with surface runoff. So our infiltration and our saturation excess. Overland flow. So when you run off on the surface, you're moving very fast, right? Stream flow is very fast. Runoff over the surface is slower than stream flow, but it still happens quickly, relatively speaking. Medium flow, and this is just in terms of time or velocity, would be that interflow or shallow surface, shallow subsurface flow. So that number 2 that we saw. And then we have slow flow. And that's going to be groundwater. So anything that gets into the groundwater is going to move very slowly towards downstream, downhill towards a stream. Now, quick flow, this is primarily what we're going to be concerned about because this is what contributes to stormwater runoff. So the peak and the volume. Our medium flow, this is important because it does contribute a little bit to volume. You know, maybe at the end of the hydrograph, it's moving quickly enough that over a storm event, it's going to contribute to that runoff hydrograph, but it's moving a little bit more slowly. And the groundwater flow, this is not going to be something we care about for storm flow. It's really just going to contribute to base flow. So important in the grand scheme of things, but not important for our stormwater runoff. Let's take a look at a runoff hydrograph. We have discharge on the y-axis, time on the x-axis, and they come in many shapes and sizes. This is kind of a stretched out one. There's a lot of ways to splice and dice this hydrograph, and we'll talk about this over the next couple weeks here. But for a simple way to think about it is that kind of leading up to it, you've got base flow, right? And then you've got some rain event happening. So rainfall happens, which we usually show as a hydrograph, something like that. And that rainfall happens, and now the stream starts to respond. You've got the surface runoff happening, you've got the medium flow, interflow happening, and so that base flow is going to rise a little bit, right, because the groundwater is rising. But a lot of this volume, so we'll say this is base flow, and then storm flow. Most of the volume is going to be in this rapid runoff. There's a lot of ways to kind of figure out what storm flow is from base flow looking at a hydrograph, and we'll talk about that in a little bit later. So there's two key variables that we're interested in. The first is the peak discharge of this hydrograph, and the second is the volume of the runoff. And this is what we're talking about today. We'll talk about Q peak later.
That one you had coming out of storm flow, that was surface runoff, you said?
Yeah, surface runoff and a little bit of that kind of shallow subsurface flow. Do you remember when we talked about macropores and like the idea that like roots and ants and moles and whatever, they dig in the soil, they loosen it up. So you actually, macropores might be really important in some areas that allow water to kind of flow, storm flow, to make it to the creek more quickly underground as opposed to the surface. So if you got a situation like that, kind of a more natural setting, that could contribute to the runoff hydrograph. Okay. So let's take a look at a figure real quick. So here's a watershed. Here's the scale down here. And you can see the drainage way. It's these hatched marks. The gray area is areas that they've identified where Horton overland flow occurs. And this is where infiltration excess overland flow is likely to occur. Meaning the soil's infiltration capacity is pretty low. So if you get rain on this soil, you know, you're definitely going to get runoff. Although you could have infiltration excess capacity happen anywhere if it for a big enough rain event, right? Some areas are going to be more sandy, more likely to infiltrate. Some areas are going to be more clay and less likely to infiltrate. So they've got the gray areas. These are urbanized areas, and it says you're going to have infiltration excess for all rainstorms. Then we look at cropland. So here's cropland areas, and so this thing about crop soil, it's pretty compacted, right? There's not a lot of vegetation or duff to help absorb the water, and so in cases like this, we're going to have a lot more runoffs. Can be pretty common, but maybe not as common as urban areas where it's paved, right? So we could still have a lot of overland flow from infiltration excess, but it's only for really large, intense storms, not all storms, right? It's not a parking lot. Then the white is zones that produce limited amounts of subsurface storm flow, large quantities of dry weather stream flow. The idea here is that these white areas have more infiltration capacity. Maybe they're sandier. So you can think of them as recharge areas. Rainfall that's going to hit these soils is more likely to go down into the water table and run off rather than running off on the surface and contribute to base flow and the stream flow. And then finally, the hatched areas are areas where we expect that water table to rise. So it's low swales and streams and floodplains. And when that water rises, it's going to be saturated, and you'll get that direct saturated excess overland flow. So these different types of overland flow play out spatially across a watershed. And also we saw that seasonally, right? You're going to have more areas that are wet during wetter periods of the season. Okay, so this figure kind of sums it all up. And what we see here is we have a lot of different factors that can affect runoff. So we have the topography and soils on this axis. On the bottom, we have steep hill slopes with deep, very permeable soils, narrow valley bottoms. On this, we have thin soils, gentle slopes, and wide valley bottoms. Then we have climate and vegetation. So arid is over here and humid with lots of vegetations over here. And so if we're in this area, we could see that Horton flow, this is the infiltration excess flow, is going to contribute to storm flow. So this overland flow is going to be more important in arid areas with a mix of steep, deep soils or thin, shallow soils. Over here, we have direct precipitation and return flow is going to dominate. And then down here, we have subsurface storm flow will dominate. So there's a lot of factors from topography to soil depth to the climate and vegetation cover that influence the runoff pathways. Okay, so let's just summarize real quick. So we'll go back to our hill slope profile, like a bigger little creek here. And we'll go back to our water table. We're under base flow conditions. And then next to this, I'm going to draw a hydrograph. All right, so right here, we're in stage 1. It's not raining. We have base flow conditions. Then we get some rain. And it's raining, it's pouring. The old man is snoring. And a few things happen. So say it's a big rainfall event, and we're going to get that infiltration excess, also known as Hortonian. So that's going to happen. So now we start to get a bump in our hydrograph. So that water is moving down the hill. Some of it's entering the soil too, right? And as it enters the soil, it's going to wet the soil up. And the water table down here, because it's raining down here, the water table might rise. So now the water table's at the surface, and we're going to get saturation excess, overland flow. Now we've got a lot of water contributing. So the hydrograph rises, and then maybe the rainfall event is past its peak. We've kind of gone through, here's a hydrograph. I'm going to draw it upside down. Just kind of a common way to draw it. So hydrograph stopped, the rainfall event stopped. So at some point we reach a peak, and then we come back down. We'll note that base flow has increased, right, because the water table increased, and then it's going to go back down to some kind of recession curve. And then this is our storm flow. So that's the idea, and we've kind of talked about all these different pathways. Conceptually of how storm flow works, and then we'll talk about two things. First we'll talk about how we might map this using GIS. So if you're taking my GIS class, we'll have a tie-in there. Then we'll take a 5-minute break and then talk about how we actually measure this stuff with the curve number method. So in GIS, we have what's called a digital elevation model, which is basically a grid, and each grid cell has an elevation assigned to it. So we can represent that three-dimensionally. And here's just a hill slope, a ridge that has a bunch of different shapes. And depending on the shape of the ridge, we might either concentrate flow or disperse flow. And there's this metric, which is called the topographic wetness index, right here, topographic wetness index. And this metric is the natural log of the upslope area divided by the tangent of alpha, and alpha is the angle in that slope. And so you can use this to identify, are you going to be dispersing water in this kind of situation, or are you going to be concentrating water in this kind of situation? This is concentrated accelerated, meaning you're kind of in a valley, but the slope is convex upwards. And here we're deaccelerating, meaning we're still in a valley bottom, but we're concave upwards. And then we have the opposite situations here. And these are kind of ridges that have different slopes downstream. So you can use a digital elevation model, and you can kind of see what we're looking at here, right? This is the top of a ridge right here, and then we have valley bottoms, and you can kind of see these would be flow paths. And instead of like a stream itself, this would be kind of runoff flow paths, and where you might have more saturated soil conditions based on the topography. So people use this type of tool in GIS to spatially model runoff, identify areas that are going to be more sensitive, like wetland areas. You could also imagine, let's see if I don't have we'll go back to this one right here. You could imagine that you got a wet area, and say this is right next to an ag field or a road or something like that. Whatever pollution or contaminants fall in this area are going to directly be contributed to the runoff. And so if you've got an oil spill or fertilizer application on a saturated surface, and then it rains, those pollutants are going to directly enter the waterway. So they're sensitive from an environmental standpoint. Not only are they typically wetland type areas, but they also are kind of hot spots for water pollutant contamination. All right, let's take a 5-minute stretch break, and we'll come back and talk about the curve number. 3-minute stretch break. Now we're going to talk about a method for estimating that surface runoff. And the method we're going to talk about is Soil Conservation Service, or SCS, now known as the Natural Resources Conservation Service. the curve number method. And this was developed by the SCS to help with agriculture, drainage, soil retention. The SCS, or now NRCS, works with producers to make sure that their soil is healthy. You know, we had the Dust Bowl and bad agricultural practices, or at least old agricultural practices, that led to a lot of topsoil loss and loss of productivity of farms. So this method was developed in light of all that. And what this ultimately is a method for calculating the volume of surface runoff. And we'll just do another. I'm going to draw a lot of these guys, so get ready for them. So the overall water balance, and this is going to be the water balance for a storm event. And so that means we're not going to account for evapotranspiration. We're going to say that evapotranspiration is going to be negligible over a multi-hour storm event, okay? So we've got precipitation coming in, we've got interception that's extracting some water, we have some infiltration happening. We also have what's known as depression storage. The idea is you've got little pools, little tiny features in the landscape that can store water temporarily. You've got return flow from the water table, and then you've got your runoff, either infiltration or saturation excess. This method does not distinguish between those. So what we want to capture then is everything that's fast to medium fast that can contribute to that runoff hydrograph, that storm hydrograph. If we write this out as a water balance equation, we have P minus what's intercepted minus what's infiltrated minus what's stored, that depression storage. And that's going to equal the net precipitation, also known as rainfall excess. Also known as quick flow from that previous conceptual talk. So in the 1950s, the Soil and Conservation Service was tasked with developing a way to estimate runoff and erosion. Stormwater flow and eroding ag fields, loss of topsoil was a big problem. A lot of this soil ended up in streams. So it was a water quality problem. There's also an agricultural productivity problem. So there's a lot of money put to this, and they looked at a lot of different fields. They measured rainfall, they measured runoff, and came up with some equations to kind of make an easy method for estimating this. So that's the idea. It's kind of a quick and easy method for calculating runoff. It's used pretty widespread. It was developed originally for agriculture in more humid areas. We do apply it out here in more arid areas, but I think it's pretty largely inaccurate. That's okay. It's a tool that we have, and we can understand its applications and uncertainties. It's since been applied for forestry, rangeland, urban hydrology, and this is ultimately what's part of this bigger method called TR55, which is an NRCS document. And this is kind of we'll call it a manual for urban stormwater. the TR55 is kind of like a bigger technical reference and procedures. The curve number method is within that. So it's kind of a step along the way. So let's talk about the curve number. It goes from 0 to 100. And at 0, we have no runoff. So that means everything is infiltrated. And at 100, we have 100% runoff. All right, so it's non-dimensional, no units. And let's just look at a quick table of curve numbers. We'll be exploring these a lot more as we go. So here's the table. This is from the TR55 Urban Hydrology for Small Watersheds. And what you see here is a bunch of numbers in a table. You can kind of go and say, okay, I've got open space, I've got impervious areas, I've got desert areas, urban districts. And you can identify a curve number based on the hydrologic soil group. So we introduced these last week. A is has the highest infiltration capacity. D is going to be more clay and have less infiltration capacity. So you can see how, depending on the open space or the land cover over here and the soil type, we have different curve numbers. And so if we have open space, you've got kind of poor condition means not a lot of grass cover, good condition means a lot of grass cover. And then hydrologic group D, we have a curve number of 80. As that land cover reduces in its condition, meaning there's less grass, more soil, that sort of thing, the curve number increases. It decreases with the hydrologic groups, meaning more infiltration capacity here. So this overall method is based on the idea of infiltration capacity and estimating that. How much are we going to infiltrate versus runoff? So here is how it works. I'm going to introduce a few terms, and then we will do the equation here. So we've got S, which is a storage index. And it's usually in either inches or millimeters, the units of it. And this gets you basically how much water a watershed, or we'll just say an area, can temporarily store. So that would be kind of depression storage, that sort of thing. Maybe it infiltrates a little bit as well. All right, so here's the equation. Q, so it's often Q. Q often means discharge, but in this case, it just means the depth. So inches is equal to precipitation, which is in inches, minus 0.2 times S squared. Divided by P plus 0.8 S. And then we calculate S from the curve number. It's kind of a weird equation, but 1,000 over the curve number minus 10. And that gets us our S. So everything else is in inches. So precipitation is in inches, and then S is in inches. Or millimeters, but I think these numbers change for millimeters. Yeah, so if you want to do millimeters, this would be S in inches, and then S in millimeters is going to equal 200, 254 0 over Cn minus 10. Nope, minus. There we go.
That number, my next one, 254.
254, yeah. We're gonna, for this class, we're gonna stick with inches for everything, but just in case you wanna use this somewhere else. And then in which case, so Q, P, and S would be in millimeters. Okay, so let's talk about how this came to be, or where do we get these curve numbers? Well, when they went out and they measured, they had, say we had a little watershed, and we had a stream in it. We had a rain gauge out there, and we had maybe a weir or something to measure the water coming out of the watershed. So we've got a ton of data. We've got a bunch of points where we have Q and P. So P is going to be our rainfall depth, and Q we can say is our the total volume over the area. So this gives us a depth. And we have a lot of points, and maybe they look something like this. You fit a line to it, just a regression. And what people were noticing is that this line never went to the origin. So we never had 0Q, right? Obviously, you would have a lot of data here, but we're only plotting data where we actually had real precipitation and real runoff. So what they noticed that there's this kind of this gap here, which they called initial abstraction. And the idea is that there's a threshold above which a watershed will produce runoff. There's a precipitation threshold. And so that initial abstraction, it's going to vary depending on a lot of circumstances, but to simplify things, they just said that your initial abstraction is equal to 0.2 S. Why we care about that is that's in the curve number equation, 0.2 S. Those numbers came from somewhere, right? When you see equations that have numbers like coefficients like this, you know it's an empirical equation, meaning it came from data and like statistical models. But the idea is that there's a threshold in the watershed above which you need to pass with the rainfall in order to produce any kind of runoff. All right, so a little bit more about the curve number method. It represents, so when we look at a curve number, I'm going to call it Cn. It represents a median value. For a given land cover type. So we saw that we had open space, right? And there's kind of a range. Maybe there's one number associated with that, but there really could be a range depending on the soil type. And so the things that affect it are the hydrologic soil group. So A is going to be a lower Cn all the way to D, which would be a higher Cn. We also have what's called antecedent moisture conditions. What do you think this means? It could be previous day or previous week, right? So if we have a rain event and it falls on wet soil, are we going to get more volume or less volume? than if it were to fall on dry soil. More volume, right? Because you're going to have more runoff. Maybe the soils, the infiltration capacity is lower. And so it's called AAMC, and you can have one. This is terminology for the soil conservation service method. And so curve numbers can change. There's a table of curve numbers that for different land uses based on the different soil moisture conditions. Is it average? Is it wet? Or is it dry? And so if we want to take a conservative approach, maybe we pick a curve number based on the wet antecedent moisture conditions. That's what happened on the 2013 flood events on the Front Range. It rained and rained and rained and rained. And then a huge, really intense slug of rain came on top of wet soils. And so you got a massive amount of runoff. So let's think about this and have you guys take a thought and then discuss. Would a curve number for, say the soil is the same, and we want to model a storm in Grand Junction, we want to model a storm in Minnesota. And say the soils are very similar, and just pick a given area in Grand Junction versus Minnesota. Do you think we're going to have a bigger curve number in Minnesota or Grand Junction? Why would that be? And there might not be one answer here. Why do you think Minnesota?
Well, I'm just trying to think of what kind of soil Minnesota has. I've never been there.
Say the soils are similar between the two places.
Climate and southern weather like.
Is it what?
What's the weather like in Minnesota?
Colder, more precipitation.
Then Minnesota would have a higher curve number. Or, yes,
Why do you think so?
because their soil will not infiltrate as much as ours.
If it's going to be more often wet, right?
Yeah.
So if you're kind of continually getting precipitation, the soils are a little bit wetter. Say it's a sandy loam or something like that in both places, then yeah, you'd have a higher curve number there. But maybe the vegetation cover is different. So you're more likely to have grass and trees and whatnot at a random place in Minnesota than you would in Grand Junction. So what the land cover matters too. So if you have the same soil and you're over on an arid area where there's no vegetation, well, you don't have any opportunities for the infiltration that vegetation allows and the interception. So you're going to have a higher curve number where there's less vegetation. So land cover is really important.